Have you ever paused, like really paused, to consider if anything in the universe ever truly disappears? Or if maybe everything is just transforming, cycling through different forms endlessly?
A massive question, isn't it? Can really make you think.
It really can. And today, that's exactly what we're diving into. This really profound idea that, well, the total stuff in the universe, it stays constant.
Right. Nothing's ever really created. Nothing's truly destroyed. It just changes, transforms.
Exactly. And what's so fascinating, I think, is how this idea, which you find in really ancient philosophy, it's mirrored almost perfectly in modern science. It's like a bridge between these worlds.
It really is.
So for this deep dive, we're looking at sources from physics, hard science, but also digging into metaphysical thought, the mission to sort of unpack how these different views maybe point to the same basic truth.
Sounds good. Let's get into it.
Okay, so where does science start with this? Physics seems like the obvious place.
Absolutely. And the cornerstone really is a principle most people have probably heard of, the law of conservation of energy.
Right. Energy can't be created or destroyed.
Precisely. It just changes form. That's the key. Energy shifts, it morphs, but the total amount, always the same.
Okay, I've heard that. We've all heard that. But making it real is harder. Like, think about a campfire. The wood burns, seems like it's gone. Something feels lost there, doesn't it?
It definitely seems that way.
Yeah.
Our senses can be a bit deceptive here.
Yeah.
So take that burning wood. It looks like it's vanishing, turning into ash.
Yeah.
You feel the heat, see the light. But none of it actually disappears from existence. The chemical energy locked in the wood, it's just transformed.
Into
heat energy radiating out, into light energy, you see, and also into the chemical energy that's now in the smoke. The gas is released and the leftover ash.
Okay.
If you could somehow trap every bit of heat, every photon of light, all the gas, weigh the ash, you'd find the total energy you started with is exactly what you ended with.
It just looks different.
Exactly. It's shifted form. Like nature doing a perfect accounting job, really.
Okay, so energy transforms, but what about actual stuff like matter, mass? Weren't mass and energy thought of as totally separate things for ages?
They were, yeah. Conserved separately, until Einstein basically blew that idea apart.
With EMC, the famous one.
That's the one. It fundamentally changed the game. It showed mass and energy aren't separate. They're interchangeable. Two forms of the same underlying thing.
So that led to a broader conservation principle.
Yes, mass-energy conservation. It means if you see mass disappear in, say, a nuclear reaction, it hasn't really vanished.
It's become energy.
A huge amount of energy, as the equation shows.
Yeah.
But the total amount of mass energy in that system, still conserved, perfectly balanced. What looks like destruction is just a really profound transformation at the atomic level.
Wow. Okay. And this even works down at the quantum level, where things get really weird. I mean, particles supposedly pop in and out of existence, quantum fluctuations.
It does get strange down there. You have these fleeting moments where particles seem to just appear, blink in and out.
So how does conservation hold up then, if stuff is just appearing?
It's actually amazing. The universe's bookkeeping, as you might call it, is incredibly precise even there. These virtual particles, as they're called.
Okay.
They always appear in pairs. A particle and its antiparticle.
So they balance out.
Instantly. Their properties cancel each other out, meaning the net energy change is zero. So even in that quantum foam, that fleeting chaos, the total energy remains perfectly neutral. The ledger is always balanced.
That level of precision, it's kind of staggering when you think about it, that the universe maintains that balance even in those tiny, fleeting moments.
It really is. It's not just that it's conserved, but how meticulously.
Yeah. And hearing about this almost perfect cosmic accounting, it makes you think about those older ideas, the philosophical ones. It feels like they were onto something long before we had the math or the labs.
That's exactly the connection point, isn't it? How did ancient thinkers without particle accelerators arrive at similar conclusions?
Right. How?
Well, through different kinds of observation, perhaps. Contemplation, looking at natural cycles. Take Hinduism, for example.
Okay.
There's this concept of Brahman, the ultimate infinite reality. Everything emerges from Brahman, lives its existence, and then dissolves back into Brahman. A constant cycle. Nothing is ever truly lost from that ultimate source.
An endless ebb and flow. Okay. And what about Buddhism? Doesn't it talk a lot about impermanence, things not lasting? How does that fit?
That's a great point, and it seems contradictory at first. Buddhism emphasizes anicca, impermanence. Everything arises, changes, passes away. Constant flux.
Well, things do disappear then.
Not in an ultimate sense. While individual phenomena, individual forms are temporary, the underlying reality is sometimes called emptiness or universal consciousness that remains untouched. Think of waves on the ocean. The waves rise and fall, they are permanent forms. But the ocean itself, the water, it persists. The total reality is constant beneath the changing appearances.
I see. So the forms change, like the energy transforming, but the fundamental ocean remains. That resonates a bit with Taoism too, doesn't it? The idea of the Tao.
Absolutely. The Tao is described as the formless source. Everything flows out from it and everything eventually returns to it. It's all about that flow, that balance, that constant transformation within an underlying unity.
And even Western philosophy.
You find echoes there too. Heraclitus, the ancient Greek philosopher, famously said you can't step into the same river twice, highlighting constant change.
Right, because the water's always flowing.
Exactly. But he also spoke of an underlying logos, a unifying principle or reason governing all the change. So even amidst the flux, there was this sense of an enduring foundation.
It really is striking, this thread transformation, not annihilation weaving through physics, ancient Eastern thought, even early Western philosophy.
It connects across scales, too, from the quantum foam right up to the entire cosmos.
Which brings us to the universe as a whole. Modern cosmology views it as, what? A closed system.
That's the prevailing view, yes. A closed system, meaning essentially no energy or matter gets in from the outside and none leaks out.
So everything that's ever been is still here, just rearranged.
Pretty much.
Yeah.
In one form or another, all the energy, all the matter that originated in the Big Bang, it's all still part of the universe, just constantly being reshuffled and transformed.
That's a huge idea to wrap your head around. So even like gigantic cosmic events, say a star explodes, a supernova.
Yep. Seems incredibly destructive.
Oh, what about black holes? They seem like the ultimate cosmic drains, don't they? Surely things are lost in there.
They certainly look like points of no return. But physics tells us the mass energy isn't actually destroyed. When a star explodes, its matter and energy are flung out, becoming nebulae, seeding new stars and planets. It's recycled, transformed.
Okay, star stuff. But the black hole?
When matter falls into a black hole, its mass energy gets added to the black hole itself. It increases the black hole's mass, its gravity. It's not deleted from the universe's inventory. It's just locked up in a different, very extreme form. Still part of the total cosmic balance sheet.
Huh. So even a black hole doesn't break the conservation rule for the universe overall.
Yeah.
Okay. But there's another law that seems tricky here. Entropy. The second law of thermodynamics.
Ah, yes. Entropy. The idea that things tend towards disorder, that usable energy decreases.
Right. So if usable energy is decreasing, isn't that a kind of loss? Doesn't that conflict with conservation?
It's a really common question, but no, it doesn't actually contradict conservation. Entropy is about the quality or availability of energy, not the quantity.
Explain that a bit more.
Okay, think of a hot cup of coffee in a cool room. The coffee has concentrated thermal energy as it cools.
The heat spreads out into the room?
Exactly. The total amount of energy in the room plus the coffee remains the same conservation holds. But the energy is dispersed. It's spread out, less concentrated, less usable for doing work, like powering an engine.
So the energy's still there, just spread thin and disorganized.
Precisely. Entropy increases as the energy becomes more disordered and evenly distributed. The total energy isn't lost, it's just less useful. So the universe might be heading towards a state of maximum entropy, maximum disorder, but the total energy content remains constant throughout that process.
Okay. That clears that up. So it really seems, whether you're looking through a telescope, a microscope, or ancient philosophical texts, you arrive at the same fundamental idea, this kind of sacred balance, maybe. Nothing's ever truly lost. It just changes its costume.
That sums it pretty well.
Yeah.
A universe of constant transformation, but underlying stability.
So think about this. Stars flare up and die. Thoughts arise and fade. Our bodies change constantly. Even tiny particles flicker in and out. It's all like waves rising and falling.
But the ocean remains.
The ocean of existence, yeah, it stays constant. The total is always the same. So here's the final thought for you, listening. If everything is just perpetually transforming, never truly disappearing, what does that deep understanding of conservation mean for how you view change in your own life, or loss? Or even what something like legacy really means?
Something to ponder, definitely.